Okay, so what we're going to do here is we're going to talk about Newton's method. All I'm going to do here is show you where the formula for Newton's method comes from. So the point of Newton's method is to try to find the solutions, the x values where our function is equal to 0, or where it crosses the x-axis. So what you do is you want to pick a point kind of close to there. I don't, just for illustration, let's say we pick this point right here. Let's call that x naught our first choice. Then what the idea here is this. You go up to your function, draw a tangent line to the function, and where it crosses the x-axis, that's your next x value. Then you go up to the graph there, draw a tangent line. This is our second x value. Then you go up to the graph, draw a tangent line. As you can see, that the point that this x value is converging and getting closer and closer to the actual value, to the solution of the root of the equation. So what's the formula that does this process? Well, what do we do here? What's the derivative at x0? Well, the derivative is the slope of this tangent line. What is the slope of this tangent line? Well, the slope is the change in y, so this distance is our function evaluated at x0. That's our y value. The change in x is this distance, x0, minus x1, leaves us with that. So the derivative is the change in y, f of x0, divided by the change in x, which I just said is x0 minus x1. Now what we want to do is just solve this equation for x1. So if I multiply both sides by x0 minus x1, on this side they cancel, and we're left with this. If I distribute, we get x0 times the derivative of f at x0 minus x1 times the derivative of f evaluated at x0. So I just distributed that. And as we can see, this is equal to f evaluated at x0. Now I want to solve this for x1. So if I move this to this side, and I move this to this side, well, when that's over there, we get x1 times the derivative. So we get x1 times the derivative at f of x0. So I move that over there. And then when I move that to the other side, we're going to get x0 times the derivative. x0 times the derivative of f at x0. And then when we move this to the other side, we're going to get minus f of x0. Right? Now again, we're solving for x1. So if I divide everything by the derivative here, we get this. As we can see, those cancel. We're left with x1. Here, again, those cancel. We get x0 minus f of x0 divided by the derivative at x0. So this is our formula. When I pick an initial point, x0, how do I find the next point, x1? Well, here's our formula. Then how do I find the formula for x2? Well, it's the same idea. You just go up, tangent line. All it's going to be is x2 is going to, these are all going to be, all of the x0s will be x1s. So in general, this is the formula for Newton's method. And you just keep going until you're sufficiently close to that point. What I mean by sufficiently close is if you want your answer to 2 decimal places, you keep doing this iteration here until your answer, the answer you get for this, doesn't change at least to 2 decimal places. But anyways, the general formula is x of n plus 1. The next x value is going to be xn, just 1 less than this number. So this is an n, minus f evaluated at xn divided by the derivative evaluated at xn. So this is the formula for Newton's method. In the next video, we'll do a concrete example of using this formula.